Hi, Rouse. I want to do some more solving examples from the end of lesson 4.2. This lesson is really important to me. It's going to be important to you. Being able to being able to solve equations is obviously a big part of mathematics, and this is going to be important going forward in our next unit and in your future courses as well. The other concern here is that this is, again, where trigonometry starts being a little bit different in grade 11 than it is in grade 10. We are going to be using our calculators as tools, but in two of these examples, out of these three equations that I want you to solve, the calculator will only give us one of the two answers. And in one of the examples, it won't give us any of the answers that we're looking for. This should not stress you out. You are going to use your understanding of these trig ratios and your sketches to solve these equations. So very important for us to understand that we're working under a restriction here, because the truth is that all of these equations have an infinite number of solutions. We'll talk a little bit more about that in our next unit, but it's more of an advanced functions topic. We are told just to find the principal angles, but watch out for that plural. Very much like our work in quadratics and our very first diagnostic that we wrote, that equation x squared equals 36 has more than one solution. Multiple solutions is a reoccurring theme. So let's dive into it. I want to figure out for what principal angles is the sine of that angle equal to 2/3. What I'm going to start with is my definition. I know that the sine of theta is the ratio of, let's go back to grade 10. If I had an angle in a right angle triangle, the sine of theta would be the ratio of the opposite to the hypotenuse. That doesn't work so great if we're outside of the first quadrant, so let's translate that to an XYR definition, and I see that the sine of theta is going to be the ratio of y to r. You may be memorizing Sir Kixertix now instead of SOHCAHTOA. That's okay. So what this means, does this mean that I know that y is 2? Of course not, because this is a sine ratio. I know that the ratio of the y value to the r value will be 2/3. But what I'm going to do is I'm going to draw myself not a triangle, but a circle of radius 3 somethings. Now this could be 3 centimeters or 3 inches or 3 feet or 3 meters, 3 millimeters. It does not matter because we're talking about a ratio. So that's 3 somethings. And I'd like to find a height, a y value of 2 on this. This means that the y value that I'm interested in is going to be about 2/3 of the way up my triangle, or sorry, up my circle. I sometimes visualize saying that if r is 3, then y is 2, as being saying, let's draw a circle that has a radius of 3, and let's draw the horizontal line y equals 2. And if you look at the points of intersection of your line and your circle, if you draw terminal arms from the origin to those points, you will have found your two principal angles. And I want to point out, once again, notice how many times we have touched the calculator so far. You want to do this before you go to the calculator. I know you know how to type in inverse sine of 2/3, but your calculator is going to give you one answer. And are you going to have to just remember that there's another answer and remember how you're going to find it? Let's just talk about how our calculators are programmed as well. Our calculator is programmed to just give us one answer. That answer is going to be the answer closest to 0. So it's going to tell me theta 1. How am I going to figure out theta 2? I see it right here on my diagram. Theta 2 is the second quadrant angle that has a related acute angle of theta 1. So I'm ready to lock in my answer here and say theta 1 is going to be what my calculator tells me when I ask for the inverse sine of 2/3. But theta 2 is going to be 180 degrees minus that theta 1. I don't need to memorize any of this. I can see it on my diagram. Let's go to the calculator now. What is, in degree mode, the inverse sine of 2/3? Before we do that, let's take a look at our sketch and see if we can make a prediction. It looks like it's about 45 degrees, maybe a little bit smaller than 45 degrees. We shouldn't just trust this machine. If I was in radian mode and I got an answer that didn't make any sense, I would want to I would want to catch that. We'll round off to the nearest degree. This means that theta 2 is going to be 180 degrees minus about 42 degrees. We're talking about 138 degrees. And those are the two solutions to this equation. Sorry, the two principal solutions to this equation. Let's see if we can sneak in the others. Switch to a cosine ratio. What if the cosine of theta is equal to negative 2/3? Let's start with our definition. Cosine of theta is the ratio of the adjacent to the hypotenuse in a right angle triangle, but if we don't have right angle triangles here, we want to translate to the ratio of x to r. It's the cosine of theta that is x to r. Please don't ever say or write cos equals x over r. That's like saying square root equals. Cosine of is a function operation, just like the square of or f of. So what I'm going to do is I'm going to draw a circle or try to find two angles where the ratio of x to r is negative 2 to 3. And getting negative ratios can be a little tricky. Let's imagine a circle. Let's pretend that the radius is, you know what? I'm not going to make the radius 3 this time. I'm going to make the radius 1, just to show you that this is not telling me that the radius is 3. It is a ratio. I'm going to need to make sure that my x value is negative 2/3 of that radius. That means that I would put my x value on my x-axis at about negative 2/3. Where's negative 2/3? It's about 2/3 of the way along this radius, and it is to the left. Okay. I'm not drawing the horizontal line y equals 2. If you wanted to imagine, make this a radius of 3, then notice I'm drawing the vertical line x equals negative 2. But again, I can make this radius 30 if I want to, and I would have to make that x value negative 20. These are not values, they are ratios. Draw your two terminal arms. And that shows you without memorizing any kind of acronyms. They're out there, I know it. You don't need them. Theta 1 is going to be in the second quadrant, and theta 2 is going to be in the third quadrant. I understand when cosine ratios are going to be negative. The cosine ratio is kind of reliable as far as calculators go. This is why you were able to deal with some obtuse angles in grade 10. Your calculator is programmed to give you the answer that is closest to 0. Both of these answers are equidistant to 0, so by default it's going to give you that positive answer. If I begin to understand how my calculator is programmed, then I am confident in saying that theta 1 is going to be the inverse cosine of negative 2/3. Now, figuring out theta 2 in the general case here is a little bit trickier. I don't know if it's really in our best interest. I could say that my related acute angle alpha is going to be the supplement of whatever this is. That's going to be 180 degrees minus the inverse cosine of negative 2/3. And then theta 2 is going to be 180 degrees plus whatever that related acute angle is. Let's just figure it out numerically. It's a lot easier to follow. I ask my calculator, stop, let's predict. We're looking for an obtuse angle. It's got to be between 90 degrees and 180 degrees. Looks like it's probably past 135 degrees, but I don't know. I'm not a good artist. Inverse cosine of negative 2/3, 135. Oh, so close. 132 degrees. There's more than one way to figure out what theta 2 is from here. You might notice that theta 2 is actually coterminal to negative 132 degrees. So you could say theta 2 is going to be the coterminal angle that I receive by adding a rotation of 360 degrees to the opposite of this angle. 360 degrees minus 132 degrees, or let's try it like this if you like. Imagine rotating, excuse me, clockwise to negative 132 degrees, but you want the principal angle. So you go forward one full rotation, 360 degrees. Either way, you'll get negative 132 plus 360, about 228 degrees. That's kind of a faster approach. I think what most students actually prefer, sorry, let me change the zoom, is actually, it takes a little bit longer, but it's kind of more reliable. Let's just find the related acute angle. You're just going to have to label your diagram and communicate to your reader what it is that you're doing. So down here, let's say I'm going to calculate alpha, my related acute angle. I'm just labeling it alpha there. That's going to be 180 degrees minus 132 degrees. Like I said, that's the supplement of 132 degrees. What's that? 48 degrees. And therefore, theta 2 is going to be the angle in the third quadrant, that has a related acute angle of 48 degrees. So that's going to be 48 degrees past 180 degrees. Oops. 180 plus 48, hey, look at that, it's 228 degrees. Now already with just 2 examples, sometimes students start to get frustrated and they say, how do I know if I need to subtract from 180 degrees or add to 180 degrees? And I'll show you how right here on your sketch. Use your sketches. Your calculator isn't going to tell you what to do, and you don't want to have to memorize, because there are actually 6 different situations we could be dealing with. Positive ratios for sine, cosine, and tangent, and negative ratios for sine, cosine, and tangent. Your sketch will tell you what you need to know and what you need to do. Okay. Let's finish up with C here. This one's a little different because, well, it's not because it's a tangent ratio that my calculator won't give me the correct answer. If I had made the sine ratio negative, my calculator won't give me the right answer. You'll get plenty of practice on your worksheet for that. Use your sketch to tell you whether your calculator will tell you the right answer or not. Okay, definition time. Tangent of theta is from grade 10. We use the definition of opposite over adjacent. Now we're going to use a more flexible definition of the ratio of y to x. So we've got a bit of a problem here. This a little bit of ambiguity, something that we're not sure about. I suppose that the tangent of theta in this case could be the ratio of -2 to +1, or any multiple of that, -20 to +10. Or the tangent of theta could be the ratio of 2 to -1. Both of those ratios would give me the answer of -2. And while it's not good formatting to keep your denominator negative, it's still possible that it's not my y value that's negative in this angle. See, what we're looking at here are the 2 different quadrants. In the first and second example, we knew that the radius was positive. The radius had to be positive. When I should have mentioned, when I looked at -2/3, I knew that it was my x value that was negative, because my radius cannot be negative. It is by definition positive. But in this case, I don't really know whether it's my x value or my y value that's positive. And I'm going to take things a little bit differently here. Since I don't see a radius, well, I could use the Pythagorean relationship to figure out what my radius is, but there's some problems there. Instead, I'm going to suggest that you just plot points. In this case, let's say if we assume that y is -2, then that means that x would be +1. And in this case, if we assume that y is +2, then x would be -1. That's a little different than dealing with a radius, but still just comes from the definition. Next change that I'm going to suggest is maybe you draw 2 separate diagrams, one for each terminal arm. It's not necessary, but I think you might appreciate it. On one of these, I'm going to plot the point 1, -2. 1, -2. And I want to stress again that I don't know that my terminal arm ends at 1, -2. Terminal arms are actually raised. They can go on forever. So I could be going over 100 down 200. It's just the ratio that is required. So we could even say this is over A and this is down to A. So there's one angle, and I'm going to hold off on labeling it because it turns out to be the second angle. The other possible position is if I go left 1 up 2. And I have discovered, not memorized, but discovered that tangent ratios are going to be negative in the second quadrant and in the fourth quadrant. I'm going to call this theta 1 because it happens before theta 2. Now, what's my calculator going to tell me? My calculator is programmed to give me the angle closest to 0. And this is a little unfortunate that in this case, it's actually going to tell me that angle. It's going to give me a negative answer. you'll have your calculator with you. You don't really need to predict what your calculator is going to tell you, but it'll help you. It'll stop you from being surprised. By looking at my diagram, I can strategize about what I'm going to do with this angle. When my calculator tells me that answer, I'm going to add 360 degrees to it to get theta 2. I'm going to take the opposite of that angle. That'll be my related acute angle right there. And I'll subtract 180 degrees by that related acute angle to get theta 1. So before touching my calculator, I already know where my answers are going to be. I know how many answers I have, and I know how I'm going to find my answers. I know this. I haven't memorized it. I know this. Okay, let's go to the calculator. Now, this is where I'm going to introduce a new symbol because I predicted, let's just say I'm suspicious. I don't think that my calculator will give me the right answer. I don't want to write down that it's a theta, so I'm just going to call it something else. I'm going to call it a beta. I ask my calculator in degree mode. I need to use it in my calculator. It is a tool that I need to use to find this value. I guess I could estimate this and say maybe it looks like about negative 60 degrees. I take the inverse tangent of negative 2. I'm on fire. It's about negative 63 degrees. Reread the directions, though. I asked for principal angles, and negative 63 degrees is not a principal angle. And you don't need to guess about whether you should add this to 180 degrees or just take the opposite of this or return 63 degrees, because we've already drawn our diagram. This means that my related acute angle is 63 degrees. So that's 63 degrees down there. This is 63 degrees back there. Theta, let's go for theta 1 first, is going to be 63 degrees back from a half rotation. That's about 117 degrees. Theta 2 is going to be 63 degrees back from a full rotation. 360 degrees minus 63 degrees is going to be about 297. Yeah. And there are my two solutions. 3 separate trig ratios, 3 similar diagrams, but different calculations to find my final answer. Sorry about the camera, Royals. Yeah, use your sketches. Okay, your calculator is a useful tool, but that's all it is. It is a tool. You do not want to be a tool. You want to use your thinking to help you find the answers.